Hello again. So this is going to take off, sorry, this portion of the class is going to take off from the end of the section on numbers and is about root finding. Now, really, I should say not root finding, but zeros, because the problem we're looking at here is if f is a function from the real numbers into the real numbers, how do we find x inside the real numbers so that f of x equals 0. Right, and we're going to talk about, or I'm going to talk about, a couple of methods: bisection, false position, and the very closely related second method, Newton-Raphson. And I'm going to have a brief look at the Brent method, just so you can see an example that is used in commercial settings. Not that these are particularly bad, but the Brent method is an extension of these methods and the ideas behind them, and is particularly good. So I'm going to talk about the algorithms. I'm going to try and write them down in pseudo code for you, talk about problems with them. Things like failure to converge, because all of these are iterative. So you apply them and then you apply them again to some set of arguments that you calculated during the previous iteration. Rates of convergence. And I'm going to talk a little bit about generalizations, but not so much generalizations. Yeah, spelt wrong. Okay. Bisection method. Right, so this approach to finding roots is based upon the intermediate value theorem. Right, so the intermediate value theorem says this: if a function f is a continuous function on an interval ab, then the minimum of fa fb, so I should say then if the minimum of fa fb is strictly less than some number u, which is strictly less than the maximum of fa fb. So that statement implies there exists some element inside the open interval containing AB, so that f of c equals u. Right, so the classic diagram here is so there's A, there's f of A, there's B, there's f of B, and the theorem claims that for any point between fa and fb on the y-axis, there exists some point between A and B that maps to it by f. So if you pick this point here, then that's your u and that's your c. So f of c equals u. Okay. So the idea is that if we happen to have a function f from the real numbers to the real numbers, and we happen to have a and b an element of R, where a is less than b, and f is continuous over the interval from a to b, and importantly, that there is a sign change, that min of FA, FB is less than 0, and 0 is less than the max of FA, FB, then we know that there absolutely exists some C inside A of B, so that f of C equals 0. We have our root. So it can be said that the interval AB brackets the 0. This is an important idea. Bracketing things in numerical analysis can avoid some issues with error. And in particular, bracketing in this way guarantees that we know where the 0 is. And you'll see some methods later on, like Newton-Raphson and the secant method, that don't do that. Because they don't bracket the root, you don't really know where the root is. You only know that you're meant to be getting closer to it, but you can't be absolutely certain of that. So that's how it works. So the point is then that you can exploit this to build an algorithm. Right. So the algorithm is, if we have, so in particular we know that one of f of a is and f of b is positive and one of them is negative. So we know their product is negative. So we have f into the real lines. We might as well assume that it's continuous between some a and some b. And f of f of b is less than 0, which is equivalent to the previous statement. Then there exists C, an element of AB, so that f of C equals 0. So we need to find it. So we can just do a search on this thing. So let m equal a plus b over 2. And we can just check, is f of m equal to 0? If it is, then we're done. If not, is f of a times f of m less than 0? So is this bit positive? Because, or at least does it have the opposite sign if there? Because if this has the opposite sign to that, then we know that if not is if so, then there is a root in the interval am. If not, then the root must be in MB. So pretty simple. Right, and then you repeat. So this looks a bit like this. You have your real number line, you have A and B, and you chop it in half. Chop it in half. Right, so if the 0 is here, there's M. Chop it in half. Chop it in half. Chop it in half. And you can see the interval gets closer and closer and closer to the root. Nice. It's very simple. Works very well. The one main restriction is that you need the signs of these to be different. So it means that you can't apply it to all functions. See if you can come up with an example of a function where it doesn't work. Okay, So talk about problems. So how do you ensure that the method finds all roots? Over the interval we know that at least one root exists, but we don't know if there are more than one root or not. There are some user errors that need to be accounted for. I mean, when you write the code, you just need to consider what happens if these two things are equal. There's a neat trick that you might have figured out. Neat trick. Have a think. It's not as hard as it might be. You might think it is. Okay, we need to write down the actual pseudocode for it, because I've just described it to you. And I'll show you the code in class. Here's an interesting one. We always halve the interval, and on the real number line it is always possible to halve the interval again. But on the computer it's not. There's a minimum interval length. So should you stop only when you get to there? Or should you stop a lot earlier? When to stop? And in general, when to stop is an important question for algorithms. And lastly, I have not proven an answer will be found. I mean, of course it will. Of course it will. But I haven't proven it. Okay. So let's do the proof first. Well, let's talk about this. Yeah, in principle it will only find one root, not all roots. And in the algorithm I checked this condition first when I described it. So it preferentially finds roots on the left. Now you could do f of m times f of b, in which case less than or equal to 0, less than 0, in which case it would preferentially find roots on the right. Okay, so there's a choice about whether or not that's good or bad, and maybe you know something about your function and you can choose what would be relevant, but it really doesn't matter. It finds a root, not all roots, so you could do an exhaustive search. When you divide up the interval into 2 bits, you could check that for sign changes on both bits, and if there are sign changes on both bits, you can trigger a new process to check one interval and check the other interval. I mean, if you wanted to. And it's certainly possible, but yeah, it only checks one. Okay, so what's the neat trick? Well, if you require this to be less than 0, then you necessarily require that a is not equal to b. So it's already accounted for. Pseudocode I will show you in class. In fact, we'll just look at some C code because it's easy enough. When should we stop? I'm going to address that, and okay, proof. Okay. Now at the same time I'm going to look at the rate of convergence, but I'm not going to describe it that way. Okay, so here we go. x0 equals a, x and y0 equals b. And we let m0 equal x0 plus y0 over 2. And if f of x is 0 times m0 is less than 0, then we let x1 equal x0 and y1 equal m0. Otherwise we let I should write it like this just to be very clear. Otherwise, if m0 times f y0, then let x1 equal m0 and y1 equal y0. So this picks the left-hand interval, this picks the right-hand interval. Otherwise, we know that f m0 equals 0, so done. So with this definition, we can say, let's just assume, and then repeat. So, mi equals xi plus yi over 2, and so on. You can write that out. Oh, sorry. So repeat mi equals xi plus yi over 2, so on and so forth. So assume that xi equals xi plus 1 equals xi, and yi plus 1 equals mi, which equals xi plus yi over 2. Right, then xi plus 1 minus yi plus 1 is equal to the absolute value of xi, because xi plus 1 is xi. So that minus, and we plug this in, xi over 2 minus yi over 2. So this is equal to xi over 2 minus yi over 2, which equals 1/2 xi minus yi. And when you think about it a little bit, this is equal to the distance of the original interval times 1/2 to the power of something. So as the limit as I goes to infinity of the absolute value, yi plus 1 equals 0. And that implies that, and since we know, since the root c is an element of the interval xi, yi for all I, then yi has to converge to c, xi has to converge to c. So that proves that the technique will work. We'll always find the root because we guarantee that the root is always in the interval, and we halve the interval at every step. Great. Okay. So as an estimate of the error left, to find the root, the 0, let the error equal the absolute value of yi minus xi. So as we just proved, the error is equal to 1/2 of the previous error for the last iteration, which is 1/2 over I0. Okay, which is great. Now, the exponent here is implicitly a 1, and that is defining linear convergence. The error term gets smaller by some constant to the power of 1. Linear convergence. Right, definition. If for some numerical algorithm the error is less than or equal to some constant times the error to the power of p, then the algorithm is said to have pth order convergence. And people use terms like linear, quadratic, cubic, quartic. I don't know, I've never heard quartic, but I guess so. Said to have pth order convergence, where ei is an estimate of the ith error. Okay, so what would normally happen is if you're searching for a particular number, this would be the particular number minus your estimate, but we're using a bracketing method, so in this case the error is the bounds on the bracket. So you'll see another way to define the error in a bit when we look at the second method. Bisection is linear, guaranteed to converge if your function has differing signs over that interval. Now it said that it takes roughly 3 iterations to gain a decimal point of accuracy. And sometimes, I haven't included it here in this particular definition, but sometimes you'll see error convergence including a measure of the number of function evaluations. So if one algorithm converges with second order and another with first order, but the second order algorithm requires 2 function evaluations and the linear algorithm requires 1 function evaluation, then some people might consider them to converge at the same rate. I'm not worrying about that here, and certainly not in this class. Okay. So the order of accuracy for a 64-bit system is, I've said many times 10 to the minus 16, but for ease, I'm going to say 10 to the minus 15, because that's kind of like 2 to the power of minus 50. So this is considering when to stop now. So definitely stop. After 50 iterations. I mean, it may very well be that the numerical error from doing the calculations has swamped whatever number you have at this point anyway. So stop after 50 iterations. That's the maximum, right? Page 6, I guess. But you may very well be doing unnecessary calculations there, right? So right, so definitely before 50 iterations. Right, and so basically you want accuracy of your answer. So the most obvious measure is pick some level of accuracy. And stop when the error is less than this accuracy. So what do you take as this thing? If you use this, then that will give you a accuracy controlling the 0, controlling the value. You're getting closer to the value, so that f of c equals 0. If you control this, then you're controlling the accuracy for the 0 itself. So, and these two things are different. So here's a function. Big 0. Big gap between these things. But so in this case, for this particular diagram, this is large, but is small. And you can think about this the other way around. take a function that's very nearly vertical, then you can end up with very small values for x and y, ending up with very big values for f of x and y. So in this particular case, xi minus yi small large. Which one's better? I mean, in this case, this is very small, so you have some idea of where the root is, but the value of that function evaluated over this interval has a large range. Is that good or bad? Depends on what you're trying to use the root for, I suppose. You can spend time making this even smaller, but you can imagine a function where in order to get this small, this has to be much smaller than the accuracy of the machine, much smaller than the step size between its number system. So, what's the point? Similarly here, this is a range that contains lots and lots of roots, while this is small. The algorithms so both the GNU Scientific Library and SciPy exclusively use this as the error measure. So absolute value, and they just say, well, if this is very large, or that's just the nature of the function itself. So the user has to cope. Could use relative error, I suppose, but the algorithms I'm going to show you, at least their coding up, doesn't. Okay, so in class I'll show the code. So for those of you who are listening to this, go have a look at SciPy. And the code is all the source code is all available online. Go to the zeros module and have a look at bisect.c, and there's some code in there that outlines in C code how bisect should work. I'll talk about it in class. You should have a look and see. Just punch this stuff into Google, you should find it. The GNU Scientific Library is a little more awkward because they have a bit more structure to their code. They have some iterative algorithm which is handled outside of the bisect code. So in the GNU Scientific Library, the bisect code comes in two parts. There's an init method which kind of sets up the various structures that are being used and checks for user input and errors in how the user is calling the function. And then there's an iterative function which is basically one step of the bisect method, and there's another function which takes these functions as arguments that performs the iteration, which is a bit different from this. So it's worth seeing. In particular, the GNU Scientific Library version of bisect is substantially more explicit, whereas the SciPy version of bisect, it's not shortcuts, but I guess the code is not as clear because GNU Scientific Library is more explicit. Anyway, go have a look at the code and you'll see what I mean. Thanks for listening.